Okay,
He's
Lean.
ready to go.
Sorry, Lean, I can't hear you.
You can't hear me? We are live.
Okay, good. So basically, I assume that I can start now. Okay, so welcome everybody on the 30th Data Science Leuven meetup. This is our schedule, and you will see that our second speakers, or two speakers that were supposed to come, had to cancel at the last moment. But luckily, we have found somebody who will replace them. And so we will also change the order a little bit. But before we come to that, let me briefly go over the program. And so the first speaker that we have today is Tim Kosemans of the University of Technology Eindhoven in the Netherlands. And he will talk about exploratory factor analysis on binary data. So Tim, I think, was originally born in Limburg and went to the University of Hasselt and the University of Ghent, and now is doing a PhD in the University of Eindhoven. The second speaker will be Philippe Daguet, who is a senior data scientist at GFK, where he sits in the global data science team, I believe. Philippe is originally from France, but is currently joining us from London. And he will talk about forecasting sales during COVID-19 and beyond. So who did we find to replace our, let's say, the people who had to cancel? That will be Chris Peters, and we all know Chris Peters from Data Minded, and he will talk about machine learning industrialization 101. And because, well, essentially, it was a late cancellation, so at this very moment, Chris is still preparing his presentation, and that's why we have switched the order a little bit. But I guess that will not make a big difference. So we have somebody from the Netherlands, we have somebody from the UK, and we were supposed to have somebody from Greece, which is quite fitting because, well, it's the Data Science Leuven meetup, and as we all know by now, Leuven is the European capital of innovation, at least according to the European Commission. Having said that, if you are listening today and watching us today, and you would like to present, and you are from the area of Leuven, feel free to make a suggestion to one of the organizers that you see here. And now we can always see whether we can find a slot to put you in. I think that as long as this Corona situation goes on, we will be in online mode. And then, let's say, one of the advantages of being in an online mode is then it's easier to get international speakers. But of course, we are always on the lookout for somebody from the Leuven area to present as well. And by the way, Chris is from Leuven, so we're doing fine in that area. So before I give the word, or the screen, I should say, to Tim, just one final announcement, and that's the 31st meetup, which will be on the 18th of November. That's a Wednesday. And I think the lineup is almost ready, and I cannot give you too much details, but for those of you who are interested in the Julia programming language, this might be something for you. And with this, I give the screen to Tim.
Thank you, Istvan. So today I will be presenting my master's results on exploratory factor analysis, more specifically for binary data. And I did a simulation, and I will take a look at what simulation-based results, what I got from that simulation, and what that means in terms of best practices. Now, Istvan already introduced me, but I'm Tim Kozmans. I graduated in business engineering at Hasselt University last year, and then statistical data analysis at Ghent University this year. And as my affiliation logo on the bottom left corner already shows, I'm currently a PhD student of marketing analytics at the Eindhoven University of Technology. Now, I'll be talking about factor analysis. As social scientists, we often aim to explain like most of what is observed with the least amount of information possible. And I will try to see like how can we adapt for factor analysis when we have, for example, binary data, which is, as of recent, like most or more often used in, for example, applied research. Now, we try to explain, as data scientists, but also as social scientists, the most of what is observed with the least amount of information possible. So we have those Y variables at the top of the screen. There are observed variables, and there's J of them. And we try to explain them using some sort of unobserved factors, some more upper-lying or overarching constructs, the etas on the bottom of the screen. And of course, there's less of those constructs, ideally, than there are variables. Otherwise, it wouldn't be of much use to, of course, use exploratory factor analysis. Now, in terms of mathematical notation, we can say, well, okay, we can propose that the Y variables, the observed variables, are a linear combination of the factors and their loadings, the lambda in this case, or the loadings, plus some type of error, some type of unique variance that we cannot explain. In matrix notation, we have the equation at the bottom of the slide, and we get that loading matrix. The loading matrix is actually what we're really after. That's what social scientists aim to uncover, being which variables load on which factors, and then how do those variables relate, and how do those variables relate to that factor. Now, under certain assumptions, we can say, well, okay, we assume that all of these, you can see it in the previous first slide, we assume that all of the covariance, all of the correlation between the observed variables is caused by those factors. That's a very strict assumption to make, but one that we're willing to make. And we can say, well, okay, we can decompose that original correlation matrix because we work with standardized variables here. We can decompose that into a product of the loading matrix that we've just discussed and the interfactor correlation matrix. Interfactor correlation matrix containing the correlations between those factors themselves, how much are they correlated to each other, and then the unique variances. The unique variances, the name kind of gives it away, is diagonal matrix. So it only says something about the part of the variance that is not explained by those factors. All the off-diagonal elements, all the covariances are assumed to be explained by the factors, and the part that is on the diagonal of that first part of the multiplication, that's what we call the communalities. That is what it's explained, or the part of the variance that is explained by the factors. Now, in case of binary data, of course, this model never really makes an assumption about the domain of those variables used. We don't limit it to the interval of 0 and 1. So people usually say, well, okay, using Pearson correlations would be quite inappropriate, and we should use the correlations. But there's never really been, or there's not been a lot of research, at least, to whether that's true or not, and whether we should really use the correlations. Now, of course, where am I going with this study? You might be wondering, well, we have these binary response formats. Usually in applied research, when we have surveys, for example, people try to decrease the mental workload for the consumers to fill in those questionnaires. If they have to answer 50, 60 questions, all with a Likert scale of 7 points, it's much too intensive. They might just answer 5 at every question and just get it on with. So we try to use binary response formats. And using these binary response formats, we still try to uncover those M1 factors, M1 being a number, well, possibly smaller than J. But in doing so, in trying to uncover these factors, we have to make multiple decisions along the way to really arrive at those latent variables. So we might ask ourselves, like, well, okay, but what is the influence of, for example, the retention criteria used, the extraction or rotation methods, and even the sample size. And that's kind of what I really wanted to investigate in my thesis. So what I did is I simulated a population from which I know the factor structure. I can sample from this population and then kind of compare the results of my analysis with that population structure. I used 20 variables, 3 major factors, and I added, which is something that I added, the formal model we've just seen, the formal model of factor analysis, and the simulation model bears a lot of resemblances, but we add the impact of 200 minor factors. Very minor factors that explain a little bit of the variance, but that aren't really worth modeling because, you know, as social scientists, we try to just see the bigger picture here. So we have the L matrix containing the loadings on the major factors that we're all used to, that's just the lambda matrix, and then also the loadings on those minor factors. In addition, we have to kind of extend that interfactor correlation matrix to not only contain the loadings between the major factors, but also between the minor factors and between the minor and the major factors. So we extend that matrix. And then it's just simulating that population correlation matrix using the equations we've seen before. So that product of the loading matrix now extended and the interfactor correlation matrix, and summing that with the unique variances matrix. We sample from that correlation matrix in a multivariate standard normally distributed way. But of course, there's a plan behind the sampling. While sampling, we vary the sample size, going from 100 observations to 1,000, 100 being kind of a small data set, and 1,000 being quite large for social sciences. And then the interfactor correlations, those are things we do at the population level. So we vary interfactor correlations from 0 to 0.5. 0, there's no correlation. These are very orthogonal factors. And 0.5, well, moderate to high correlation. Communality is also something that we vary from a weaker factors, so a range of 0.2 to 0.4, to a very strong factor of 0.6 to 0.8. Communalities, remember, is the part of the variation that is explained by the factors. And then we analyze the data that we sample, of course, from that correlation matrix in a few different ways. Continuous data gets, or as a result of that sampling procedure, and we can analyze it as continuous data. We analyze it as dichotomous data using a 50-50 split between zeros and ones, because that's usually the more realistic, or that's usually the most academic way to approach things, but also using a 75-25 split between zeros and ones, because we usually see in practice that that is what often happens. And then those last two dichotomous cases, we analyze those using both those Pythagorean and Pearson correlations to really see if that really makes a difference. And for each of the scenarios, we do that 1,000 times. So we have some scenarios defined by the sampling part on the left, which is 2 by 2 by 2 design. We do it 1,000 times. And then we get to, okay, what do we recommend? What do the results give us in terms of recommendations when it comes to retention criteria, extraction methods, and rotation methods? Let's first focus on that retention mechanism. Often these criteria are based on the eigenvalues of the correlation matrix. That's something that is, comes from a long way back from the 1960s, and not all of these criteria are unbiased, and there are newer methods and often more unbiased methods that we can use. The ones on the left here, highlighted in the black, those are based on the eigenvalues of that correlation matrix. So we have the Kaiser criterion, which just says, well, okay, let's take the eigenvalues of the correlation matrix and let's take the amount of factors for which the eigenvalues are greater than 1. The scree plot, plots these eigenvalues and looks for the elbow in a sequentially plotted eigenvalues and takes that number -1. And revised parallel analysis or traditional parallel analysis compares the eigenvalues of our data to that of completely random data that we generate ourselves with or without an underlying factor structure. Those are all eigenvalue based. And then there's two more exotic methods, more or less used methods. The minimum average partial method, which says, well, okay, let's filter out one component after another. And then let's look at the partial correlation matrix. What kind of correlation remains? And then let's say make a summary measure of the correlation matrix, the average squared partial correlation, and look where this is at a minimum. And that is the optimal amount of factors to retain. Exploratory graph analysis, on the other hand, is a quite recent procedure from, I think, 2017, which thinks of variables as a network connected by edges, and the best number of factors, or the best number of clusters in this case, is the one that maximizes what they call modularity. Now, in terms of retention criteria, what does this mean? Well, from this analysis, we save some results, how many factors we have to save, etc. We run a few models and we assess the accuracy of the different retention criteria in the different scenarios defined by the sampling procedure. And we see in terms of results that when working with continuous data, eigenvalue-based criteria, so those that are most often used, usually underperform. Revised parallel analysis is good, but only in small samples, and exploratory graph analysis, that more exotic recent procedure, is actually always a good idea. Moving to dichotomous data, we see quite contradictory to what is knowledge in this domain, that tetrahoric correlations actually lower the performance of all of the criteria, so that we advise in this first stage to really use Pearson correlations. And also that there's no real influence on the split between zeros and ones. The same holds for extraction methods. How do we extract those loadings? People often use principal components analysis as a replacement for exploratory factor analysis because, well, for reasons we'll see in a minute. But exploratory factor analysis itself can also be conducted in several ways, as we'll see. So there's a few criteria that I tested. We have PCA. It's less computationally cumbersome, as we might expect, because we can set all those communalities by definition or by default to 1. That's what PCA does. And it says, well, very easily, the loading matrix is equal to the product of the eigenvector matrix multiplied with the square root of the eigenvalue matrix, which is very computationally not very cumbersome, very easy and straightforward to do. OLS, on the other hand, is proposed to be better for weaker factors because it minimizes the sum of squares between the observed correlation matrix and the reproduced one. And MLE, maximum likelihood estimation, as we all know, is consistent, has minimum variance, has also the benefit of having some statistical tests attached to it, but also has some distributional assumptions, although it is hypothesized that those methods, of course, are quite robust to deviations from those assumptions. We maximize the likelihood in this case, which has, well, that format that's displayed there. And what do we see again? We say from those loading matrices that we get at the end of our analysis some summary measures that allow us to see how accurate this correlation or this loading matrix is. We run some models and again assess this accuracy. We see that maximum likelihood estimation is actually overall the best method to use when working with continuous data. And that PCA and OLS, although ordinary least squares is exploratory factor analysis in the purest form, actually perform largely equal in terms of accuracy. And moving to dichotomous data, on the other hand, we see that OLS is a preferred method, not only when there's low communalities, but also when there's low sample sizes. So low sample size of 100 in this case, and also when the factors are kind of weak. And then we also see that using the tetrahoric correlations in this case now does reverse the negative effect that a Pearson correlation has. And then we see again that that split between zeros and ones is kind of trivial. It doesn't really have an effect. The last part that we do in factor analysis is rotate that matrix. Why do we rotate it, you might ask? Well, it's to achieve perfect simple structure. We try to achieve a matrix that is almost in a way as sparse as possible, where we say, well, okay, we want as few high loadings for every variable as possible and as few variables as possible to load on each factor. In this case, we can see we do an orthogonal, that's a graphical rotation that I see on the screen, where we have, in the unrotated case, mediocre loadings on both factors for variable 1 and 2, v1 and v2, but after rotation, we only have high loadings on the rotated factor number 2. We can do this in two ways, using orthogonal rotations, which do not allow for interfactor correlations, but they're not very realistic in this day and age. And then oblique rotations, which is more realistic. How do we do that? That rotation, there's rotational indeterminacy. We can redistribute that variance a little bit. And usually, back in the day, it used to be done very graphically, which is, of course, a very time-consuming procedure. So people have established mathematical criteria that, for them, represent a perfect simple structure. So we can rotate the original loading matrix, the A matrix in this case, using a transformation matrix T. This T matrix we can choose from an infinite set, but it has to adhere to some restrictions. So in case of the oblique rotations, when we take a diagonal of that product, it has to be an identity matrix, or if it's an orthogonal rotation, of course, it has to be an orthogonal matrix. Now, again, I said simple structure is defined differently by different criteria because it's not done graphically anymore, but we can kind of maximize or optimize this certain criterion in terms of that matrix T. How do we optimize that? Using something probably most of you already know, using the gradient projection algorithm, which is a combination of the gradient descent algorithm, but also always keeping in mind those restrictions that we imposed earlier. So it's kind of a variation on that algorithm. And then we see, okay, we have these body max rotations. If you've ever done exploratory factor analysis, you probably know from the body max rotation, it's the most well-known orthogonal rotation method. It's also the most used. And then the Quartim and the geomin procedures, they're both oblique rotation methods. Arguably, they're more realistic, and they're the most well-known oblique rotation procedures. What do we see again? We get those loading matrices. We save some results regarding accuracy, run models, and assess accuracy in different scenarios. We see, well, okay, the geomin and the quartimin, in case of continuous data, are quite comparable procedures. And the Vadimax rotation, it makes this assumption of no interfactor correlations. So, of course, we expect it to do good in scenarios where there is no interfactor correlation. But we see that the Vadimax rotation is actually only a justifiable choice when also communalities are low, so when factors are weak. In all other cases, it's better to use geomin or quartimin rotation. What we also see is that it's not because we get an oblique rotation procedure and we get a loading matrix that is more accurate that our interfactor correlation matrix is also more accurate. It can be quite off, and that was usually due to one or two negative correlations in that correlation matrix for some reason. Then when moving to dichotomous data, we see that if we use the tetrachoric correlations, we get identical results, and there is again no split, or there's no effect of this split between zeros and ones. That's quite a lot. That's quite a lot to take in, I think. So let's finish with a conclusion and with some key takeaways. So if I want you to remember one slide, it's going to be this slide. If you ever do exploratory factor analysis again, please remember that eigenvalue-based criteria, when talking about retention, usually underperform. Exploratory graph analysis is almost always recommended, and it's very easy to implement. It's just one package in R that does all the work for you. Also remember that when you use Pearson correlations in this first stage, it actually gives you better results. When moving to extraction and rotation, we see that this common knowledge already had that PCA is not a substitute, that maximum likelihood estimation is preferred, and ordinary least squares is actually preferred for weak factors in small samples. Of course, you don't know this on forehand if you have weaker factors or not, so you might just want to use maximum likelihood estimation altogether. And also use the tetrachoric correlations in this case. What we also see is that in terms of rotation, orthogonal procedures are not very realistic. We want to allow for some correlation between the constructs that we find, especially in the social sciences. That's going to be the case. So please do use geomin or quartimin procedure, even if your factors are mostly or almost completely orthogonal. A oblique rotation procedure would normally also then return correlations that are close to zero. And use the tetrachoric correlations also in this case. Regarding sample size, we see that under these best practices, so if you would follow the three things that I just said, that there's no real influence of sample size. So that sample size doesn't really matter whether it's 100 or 1,000, you can still receive very accurate results. And that's all for my presentation. So if there's people who have questions, I'd be glad to answer them, or remarks, or things about, or limitations that I might have to think about in future studies. If you don't want to put the question here, you can also always contact me at my email address, or on Twitter, or on LinkedIn. I don't know if there's any questions.
Istvan, I'm afraid you'll need to unmute yourself. Wait, can I do it?
Yeah, because you did it as well. Okay, thank you. So I'm sorry, I was on mute. Thank you, Tim, for this interesting presentation, especially because your findings are, let's say, challenging the common practices that we see in social sciences mostly, and also in more applied settings such as market research. So I'm trying to see whether there are questions. I'm a little bit confused. Lean, I don't know whether you have seen any questions out there. So in the meantime that we figure out whether there are some questions, let me ask one for myself. So Tim, it struck me that you, every time, even in your introduction, you mentioned social sciences, which is something that I like, obviously. But a lot of our audience, let's say, are not necessarily from the social sciences. So do you have, in your experience, because I think you're now, when you were studying in Ghent, for example, you were within general data science, so not necessarily tied to the social sciences. So I'm sure you've also talked to biologists and so on and so forth. So do you have any view on how, let's say, people who have a more positive scientific background, how they look at these things?
Well, that kind of depends. Of course, there's a lot of talk about, for example, the rotation methods. So the oblique versus orthogonal. Usually in principal components analysis, your goal is to do data reduction, and you want your components to be orthogonal because that's, well, easy if you're going to do principal components regression or something. And even then, in that case, I think, Istvan, you sent me the paper on that. The Weiermarx rotation can be kind of something that allows you to make a matrix more sparse, for example. If you rotate it and you see very, very small loadings, that makes the loading matrix more sparse. So although exploratory factor analysis is something that is very much related to the social sciences and to uncovering constructs, I do think some of the methods that are presented here, for example, those rotation methods, but also the exploratory graph analysis to see how many components you might want to retain, etc., are certainly transferable to other disciplines.
All right, okay. And I see, I'm now switching, I see that Peter Coussement of Coussement, sorry, I'm switching languages here. No, it's Anthony Coppens who has a question. What's your best practice in interpreting the factors?
The best practice interpreting the factors, well, you usually look for factors, for interpreting the factors, for the items that have high loadings on those factors. And when you see those high loadings, you can kind of, based on the wording of the questionnaire, on what the items really are, you can kind of name the factors too. So there's, in naming and interpreting the factors, that's actually where there's no real way of evaluating which procedure is best, because that's a very subjective thing to do. So in naming the factors is just always looking at which items have high loadings and using the wording of those items to name those factors in very, very names that kind of really speak to you, that are comprehensive and kind of summarize which items are beneath that factor. I hope that's what you were asking.
Okay, now let me see if there's a final question. It's always very confusing when I switch to YouTube. It has a delay. But as far as I can see, there are no further questions. So, Tim, I would like to thank you again for your presentation. And indeed, if people have some additional questions or things that they would like to discuss with you, your contact information is there, and I guess they can reach you directly.
Yes.
Okay, this brings us to the second speaker today, and that's Philippe, who is joining us from London, but I'll let him introduce himself. Philippe, the floor is yours, or I should say the screen is yours.
Yes, thank you, Istvan. Can you hear me well?
Yes, I can.
Okay, so my name is Philippe Dagger. I'm a senior data scientist at GfK, and I'm going to talk about forecast today. But let me first start with a few words about what is GfK. GfK is a market research company. What makes GfK really special? I mean, we are one of the leading market research company. We collect point of sales data from almost every retailer in the world. I mean, and wherever we do not have the right data, we have the possibility to extrapolate this data to make it as much representative as possible. So we provide our customers insight about brand values, about price, about recommendation on assortments, and here specifically about forecast. So what makes forecast specific nowadays? Definitely it's the COVID crisis. Before the COVID crisis, when you look at time series data related to products, then these time series are pretty much trendy, seasonal, and very easily predictable. Most of the people tend to use last year's data in order to forecast what's going to happen in the coming weeks or months. But since the COVID crisis happened, it's pretty much difficult to tell what's going to happen next. Most of the retailers and shops were closed during the lockdown. As you can see, this is the kind of shape that we have for a time series related to the sales of a product during the last few weeks. So during this presentation, I'm going to share with you some of my work in forecasting at GfK, the way we are trying to solve the problem, the modeling approach that we adopted, and some of the results that we have obtained. So again, I mean, what do we do at GfK? We are mostly specialized in what we call white goods and brown goods. This is typically what you see in this basket. So cooling equipment, washing machines, audio home systems, etc., etc. So we try to provide our customers with a perspective about the quantities that will be sold, or the amount in revenues that they will have in this particular market. And the time horizon, of course, it could be a few weeks or several months, depending on the need. And what's particular about GfK is that we are collecting a lot of things about these markets. We know about the number of the items that have been sold, the brands that are sold. We know about the channels, the retailers, the outlets. We have a view about a huge number of product lines and segments within each one of these product lines. And then we have a coverage of almost most of the countries. So when I started this project a few months ago, we started a pilot in 15 countries covering more or less 50 product lines. So a combination of a country and a product line is what we call a market. And then we were looking more specifically at the online and offline channel, so offline stores and e-commerce. I should say that each one of these markets represent more or less on average 250 brands. So which means that we have more or less 50,000 time series to deal with. These time series are about quantities, about revenues, about the number of active items in each one of these markets, and also about the number of active outlets in each one of these markets. So the purpose is to provide our clients with a short-term forecast, 12-week forecast, to help them respond to some immediate needs, specifically supply chain managers, in order to adapt and adjust their operations to the market fluctuations, and also brand managers to adjust their budgets and their specific spends to achieve their targets. So the way we dealt with this is that we wanted to rely on some external factors that will help us understand the context in which we are navigating, hoping that we can learn from this context in order to provide a more accurate forecast given the situation. So the external factors that we studied are Google Trend data, some indexes provided by the Oxford University. It's an API called Coronavirus Government Response Tracker, some other macroeconomical data, and of course, user feedback when possible. So just very quickly, for those who are not familiar with the Government Response Tracker, typically Oxford University is compiling a set of information related to how government are responding to the crisis in order to contain this crisis. A lot of this information is published on their website. There is also some nice visualization on our world in data that I can demonstrate to you very quickly. Like, for example, here we have the stringency index, which represents the level of containment that each one of the countries is applying starting January. So it's an index from 0 to 100, 0 being the minimum. It's what we had before the crisis in January. 100 is the maximum. And here you can see very quickly in this simulation how this index is actually varying with time across countries in the world from January to October 22. So this kind of information from the Oxford University is updated on a daily basis and is provided, of course, publicly. A lot of people have been using it in order to study the evolution of the pandemic. We have other type of data as well collected and aggregated within the same API. It's, for example, the number of cases or the number of deaths that is also available. In our case, we are interested in the weekly information. And as you can see here, for example, the number of COVID deaths that is available starting January this year until the most recent date. So this is one source of data that we have been relying on very heavily. This source of data is being increasingly more and more complex, with insight about some tiny details about how governments are managing the crisis, about how they are containing things from a hospital perspective, from a financial perspective, etc., etc. And all this data is, of course, available for public use. The other source of information that we relied on is Google Trend data. In this case, we wanted to understand how the population is behaving given the crisis. So we try to identify some keywords, some topics that can relate to the way people are dealing with this crisis and how it is impacting their daily work. Like here, I'm giving you a very short example about a topic that is called telecommuting on Google Trend. It is equivalent to what we commonly call work from home. And as you can see, the interest in work from home in France was very little before the crisis. And all of a sudden, when the lockdown happened, the interest in work from home has risen to the maximum, and now it's being fluctuating between certain values. So this is the kind of information that we wanted to use. And one of the particularities, by the way, when we use this kind of external data is a lot of time this external data is not comparable between countries. Specifically, for example, when we deal with Google Trend data, Google provide normalized data between 0 and 100 per country, which means that if we are for work from home at a level of 50 in France, it doesn't have the same meaning as the level of 50 in Germany. So it is very important later on to understand that we need to pre-process the data in order to make it comparable to each other. It is the same as well, for example, for the number of COVID cases or the number of deaths cases related to COVID. We all know that countries do not measure this information in a similar way. So the data that we collect from different countries is not comparable. And then we need to deal with this situation in order to be able to use it in a model. So so what is the problem that we are trying to solve? We would like to have a short-term forecast for brands. So again, we want to provide a forecast for a market. A market is a product line in a country. So the way we wanted to approach the problem is from bottom up, and the bottom being the brand. So which means that we're going to try to forecast at the brand level and then aggregate the forecast at the brand level into the market level. So problem formulation is we are going to forecast brands for the next 12 weeks, given, of course, all the information, the historical information that we have about the brands that we are collecting at GfK, but also given all these external features that we are trying also to extract from different sources. We have also information also within GfK about outlets, about items, and this information is also aggregated at the brand level in order to be used. But also, and most importantly, and in order to succeed in such a difficult task about predicting the future, we need to use as much as possible information about the coming future. Some of the information is known, is real. Like, for example, if Amazon decide to schedule a Amazon Prime Day in the next 2 weeks or the next 3 weeks, so it is a known information about the future that we definitely need to pull into the model. And some other information are estimated, like, for example, about how the pandemic is going to evolve in a given country, given how people are estimating this situation, or some other feedback that could come from our clients themselves about how they feel the market and how they would like this information to be injected in the model. So this is what we call the future context. So what do we have as data? We have some static data representing the country, the product line, the channel that we are dealing with, online or offline, and the brands. We have some behavioral data related to the quantities, to the price, to the channel split, to the market trend in which we are evolving, to the yearly trend, to the yearly cumulated trend, to the active items, to the active stores, and also we have all these indexes that we pulled from the external sources. But most importantly, we have these look-ahead features that we have estimated or we already know. So again, we are working on a weekly basis, so which means that we collect all this data on a weekly basis, and we try to predict the future 12 weeks. For all these time series that we collect, we're going to apply subsampling because the objective is to develop a deep learning network with a specific input size. And this subsampling technique will allow us actually to have an understanding of the time series at different period of time. As you can see here, the green window represent the past information, the red window represent the future information for a specific subsample. And this subsampling is going to happen with a slide of 6 weeks in our case. The past information is typically 52 weeks. This is what we try when we try to look into the past, and the future information is 12 weeks. This is when we try to look into the future. So this will allow us actually to build a data set of a 4-dimensional data set. The subsample actually expanded our original brand time series data from more or less 50,000 time series to more than 350,000 subsampled brand time series. We have a second dimension, which is the 52 consecutive weeks. The third dimension is about all the features that we are dealing with, and the fourth dimensions are the future information, the 12 weeks future at each time step for each one of these features. Obviously, the target that we are trying to predict has also the same structure. The target, which is a unit sale, is available for each one of these 52 past weeks. And for each one of these time steps, we have the future values that we will be learning from during the training of the model. So the challenge, of course, is to package this information in a 4D tensor, so we will be able to use it in a model later on. So we're not going to train all the markets and at the same time, which means all the products and all the countries at the same time. We're going to cluster them in similar geographies and content. And of course, we're going to evaluate the performance of the training based on a mean absolute error at the brand level. And then when we aggregate up to the market level all these granular forecasts, we're going to use MAPE, the mean average percentage error, as a way to challenge the performance of the model. The baseline being, until now, of course, the prediction that I already discussed with you that is commonly used in this business, which is using the last year's values as a forecast. And the model that I'm going to discuss with you later on now is actually a combination of a feature extractor, which is an autoencoder, and a forecaster that is based on a Wavenet approach, and also a feedback loop that is using a 2D convolution in order to parse the future vectors and adjust the initial output of the Wavenet model. So this technique of using a feature extractor and then a forecaster is taken from a Uber paper that is called Time Series Extreme Event Forecasting with Neural Networks. It was published in 2017, so it has been commonly very widely discussed in the community. The idea that I would like to retain is that there is an autoencoder that is simply an LSTM autoencoder that is going to take these subsamples of multivariate time series and try to learn how to encode them and predict them. So this process is going to allow us to have an encoding mechanism that will generate features. These features are going to be concatenated to the original input data in order to enter a Wavenet model that will try to predict the future 12 weeks. And the reason we chose the Wavenet model is again, I mean, the paper was initially based on an LSTM architecture. The reason we prefer the Wavenet is that because we had long time series of 52 steps, and we wanted to capture the particularities over time of the entire subsample. One thing maybe I would like to mention, and that is particular to this design, is that the autoencoder has a heavy dropout rate, which means that each time we call with the same subsample the autoencoder, it will generate a different set of features. And this will allow us actually to bring to our forecasting approach an uncertainty, because the way we are going to showcase an uncertainty is by forecasting for the same brand multiple times, and then try to have a minimum, a maximum, and also a median value for the forecast. So what is the particularity that we brought actually to this design? The particularity is twofold. The first one is the fact that the input data that is coming from different countries is not comparable. So we need actually to make it comparable. So we created at the input level a transformer that will take the data that is not comparable and modify it given the country to which it belongs, in order to make it ready for the input of the proposed model. So this is what we call the equalizer. So the equalizer is a transformation that is going to take, for example, a Google Trend data and the country that to which this time series data belongs, and transform it into another time series that is going to be comparable to time series from the same category. So this is one modification. The second modification is about the feedback loop. So the purpose of the feedback loop is to allow actually to use the information of each, the information of the future of information of each time step. So again, we have 52 time steps. For each one of these 52 time steps, we are trying to predict the future 12 time steps. So which means the mean squared error that we are trying to achieve is going to work across these 52 times 12 values that we want to predict. So not only a prediction at the last time step, but for each one of the historical time steps. Now, what happens is that each one of these features that we are using has a future value. But let me take one very simple example. One feature, for example, that we are using as an input data is the week type. So the week type, or in a general way, it's the position of the week in a month. It's from 1 to 5, so it's a label. But then we have some special weeks, like the weeks that where we have, for example, events like Black Friday, like Cyber Monday, like Amazon Prime Day. So these events are different categories, and these weeks are going to be embedded, and they will be they are used also as features at the input level. But then we know also what will be the future week for each one of our input data. Sorry. So in this case, we're going to use this information in order to create a factor that will come and multiply or amend the initial output that is coming out of the forecaster. So this, in order to create these factors that will amend this output, we're going to parse the representation of these future weeks using a convolutional 2D. So again, these future weeks are available for each one of these 52 steps. We have 12 of them at each one of these at each one of these 52 steps, and then we have projected them into a latent space using the embeddings. So consider that, for example, we have a latent space of 3, which is similar of having, for example, 3 channels in an image. So we are going to parse these 52 times 13 times number of channels in order to generate these factors that are going to come and multiply the primary output of the forecaster. And this will give us the adjusted forecast. So this is valid for the example that I gave with the categorical features, but also it is valid also with the equalized input, because the output of the equalized input is also multidimensional, and it has the same size of the embedded features. So all this is concatenated at the output level and then parsed with a convolution 2D that is creating factors that are multiplying the primary output in order to provide an adjusted forecast. So this is how we are able today to deliver this kind of forecast post-COVID. So this is a result that is related to a forecast that we generated beginning of July. In red, you can see the forecasted data with the uncertainty that we discussed, coming from the fact that we have a dropout rate, and we are able to provide multiple values. The green line is the true data that happened meanwhile. And of course, the challenge of our approach is to see how it will work with the coming Black Friday. We have backtested the Black Friday last year, of course, prior to the COVID period, and it seems to work quite well. So the challenge, of course, today is to see whether our forecast will really cope with the reality that is going to happen in the next few weeks. So that's it for me today. I hope I was clear enough conveying these ideas to you, but let me see if I can answer most of your questions now, and
Okay.
maybe I can say is that GFK is hiring. If you can either contact me or go to our website for any opening.
Okay, thank you, Philip, for that. Let me quickly switch to say, okay, I see a couple of questions. I see Koen van Parijs, the legendary Koen van Parijs, who asked, could you elaborate a bit more about equalizing data from different countries? Are Google Trends data 0-1 calibrated between countries?
So let me maybe show an example of Google Trend data. Google Trend data, when we go to the website and then we select, for example, a topic, we have here topic telecommuting. Then I select a country, and then I select the number of years for which I want this data, and then I get this kind of result. And this result is always between 0 and 100. So when Google provides the data for a specific keyword and a specific countries, it always provides a result between the minimum and the maximum, putting the minimum at 0 and the maximum at 100. So if I now request another country like Germany, then the same, I will have the result between 0 and 100. And obviously, the 100 of Germany has nothing to do with the 100 of France. So which means that somehow we need to revert this data to its original scale, so that when the model is learning from this data, it is learning from comparable information. And this is where this is the role of the equalizer, actually, is to learn a transformation that allow the data to come back to its original scale. I hope I'm clear enough.
Okay, thank you. I see that Koen has a follow-up question, but let me first go, if you don't mind, to a question of Anthony Coppens, who has an interesting question. How are other algorithms such as regression with ARIMA errors are also considered? The reason why I find this an interesting question is from a commercial perspective. Oh, and I see that Lean has copied the question. Thank you. So and I'm from GFK as well. So from a commercial perspective, it is interesting to tell to your clients, look, what we are doing here is, let's say, better than, let's say, what our competitors would have done. So do you have used, let's say, more traditional methods as a benchmark?
Yes, of course. I mean, before we started this project, we had already a tool that is based on ARIMA that is working within the toolbox that we provide to our customers. It's been working here for several years now. And the reason we started thinking about something different is simply because this tool was not providing the kind of accuracy that our customers were expecting during the COVID crisis. And specifically because we needed to take into account so many external factors, and also, I mean, really what triggered the success of this new approach is the ability to have a feedback loop that is pulling some information from the future into the model. So definitely it's a question of performance. We tried different approaches. There are a lot of solutions out there. We almost tried all of them, and then we benchmarked this model with at least, I would say, 12 or 13 other models. Yes.
Okay, thank you. So let's go for one small final question, and indeed you can read my mind. The question of Koen van Parijs. Go ahead. So it has to do with data from GSM, mobile phone movement data.
So what is the question? Sorry.
Oh, have you? Oh, you cannot see it. So the question is: have you also considered using mobile phone movement data? As you mentioned that you are using external data. So Koen is asking: did you also use mobile phone movement data or other proxies?
Yes, as a matter of fact, we have considered a lot of possible data. The problem with some of these other sources is that they are not available worldwide. And we wanted a solution that we can deploy in almost every country in the globe. So very often this mobile phone data is available in main countries like Germany, US, maybe a few European countries. But if we want to extend, for example, to Latin America, to Asia, then it is becoming a great challenge actually to have access to this information.
Okay, good. And I see that there are some other interesting questions. Unfortunately, we don't have the time for that, but I saw, for instance, an interesting question from Carrie Chow. And I suggest, Philippe, that you have a look at afterwards at those questions as well, because I think they might be interesting. Which brings us now, Lean, if I'm not mistaken, now it's time to move to our third speaker, and our third speaker needs no introduction, huh? So I will not give an introduction. As simple as that. It's Chris Peters, who last month was sitting in my place in his house, obviously, but okay. Chris, go ahead. And you are on mute, I think. You're still on mute. I think you're still on mute. I cannot hear you. Lean, I think I can hear, I can't hear.
Yeah, Chris had some connection issues. He's
All right.
Is this better?
He's back. Okay.
Can you hear me
Let's
now?
start again.
All right.
Yeah. Can you speak up a little?
Yeah, I can. Sorry. Yeah, there's something wrong with my mic. This is happening a lot, apparently. Anyway, thanks for giving me the floor. This was a very last minute presentation. I reused a presentation that somebody else at our company did. So I hope it's going to be useful. All right, I'm going to share my screen. All right, you guys see my screen, right? I guess so.
Yes, we can.
All right, cool. So I'm going to talk about ML industrialization platforms. We're at Data Science Leuven. My name is Chris. When I'm not at Data Science Leuven, I actually work for a company called Data Minded. So what is ML industrialization platforms? What are they? Well, if you look on the market, there's actually quite a lot of ML platforms out there, like Dataiku and Kubeflow and Weights and Biases and whatnot, MLflow. There's a million out there. We compared the three big cloud offerings out there. Like we looked at Azure ML, we looked at Google AI, and we looked at Amazon SageMaker, and we saw a bit like, okay, can these tools, can they be valuable if you're doing a machine learning project? How can these tools help you, and how can they industrialize your ML code? So you wonder a bit, what do you mean with industrialization? I guess since this is a Data Science Leuven meetup, everybody knows by heart the data science life cycle, right? No, but this is a good picture that describes, like, typically if you want to do data science, you start from business understanding, then you go to building a data understanding, and maybe sometimes brings you back to business understanding. But anyway, from that data understanding, you do some data prep, you do some modeling. In the end, you evaluate if your model is good enough. If your model is not good enough, you go back to business understanding because there's something wrong there. Maybe didn't understand what the business needs were, or you didn't have the right data, or the model capabilities weren't strong enough. Or in the very best case, how they depict it in this model is you go to a deployment step. And they just make it very simple. You deploy the model and that's it. But actually, this is a very scientific view of looking at data science. If you look at data science from a business point of view, so if you ask your head of data science or head of analytics or whatever, chief data officer to look at this is what that person sees. That person sees, okay, I need to build a business understanding that's going to cost me a lot of money because it's going to cost me a lot of time of my people. Creating data understanding is going to cost me even more money. Doing data prep is a bunch of engineers and scientists hacking on their laptops, so that's going to cost me money. Modeling is going to cost me money. Doing the evaluation is cost me money. And the deployment, actually doing a deployment is just a technical thing, so that's also going to cost you money, right? So why are people even doing data science projects if all it does is costing you money? Well, and there's two things that can happen once you deploy your model. You see that the market really doesn't care about your model at all, and then you burn some more money to host it. And there's only one hallelujah moment, I would say, one nirvana moment, that if you see there's user adoption for your models, then hopefully you're going to gain money, right? You're going to gain money by reducing churn or by doing better recommendation about next best product to buy or whatnot. Whatever your data science algorithm does, if it does it well, you're going to create money, right? And that's an important thing to note. Like if you put away or you take off your science cap and you put on your business cap, is that when you talk to business people about data science, they really care about you putting stuff in production, you deploying stuff that actually is going to give you user adoption, actually going to bring the business money, right? All the rest they honestly do not care about. They might like to use all the buzzwords in talks like this, but in the end, they care about the money when there is user adoption. So how do you go about that, right? So you cannot just quickly, step one, create adoption and then be done with it, right? It's a step-by-step process. And actually, every machine learning project that we've seen, you can plot on two axes. So if you think about, you need some kind of experimentation phase where you just hack around and try to find is this model valuable enough to be deployed? And sometimes that's yes, sometimes you turn out like a lot of hacking around, you see that the model is not valuable at all. And then on the other axis, you have industrialization, like once we've seen that model is valuable, now it actually needs to be run somewhere in production. It needs to be linked with operational processes. It needs to be connected to your, I don't know, to your marketing automation system or whatnot. So there's two approaches on how to walk through this landscape. Is one, you start with industrializing what you have. So you set up big processes, you connect big machines, and you focus on operational excellence. Before you even proven the value of the model, you kind of assume that will work, and you focus on industrialization first. That's a naive approach, right? Because you can spend a lot of money and then realize that the model is not bringing any value or any money, and then people get very disappointed. So what is a better approach is that first you focus on finding that business value, proving that yes, if we deploy this model in production, we're all going to be filthy rich and everybody's going to be happy, and I get 10 extra people on my team, right? So definitely that's the first recommendation you want to do. When you think about industrializing your model, it is an important step. It is the step that will bring you money, but that still means that first you have to go through an experimentation phase, right? Do experimentation first before you start industrializing. So what are some of the things that we see going wrong in the experimentation phase? If you go from left to right, you go from startups to large organizations. Typical things that make your experimentation phase fail is that you don't have the data you actually want. You have budget restrictions. You don't even have data scientists on your team. It could be you don't have any infrastructure. Maybe you're just doing it on your laptop, which is kind of hard for experimentation. If you've done a lot of experiments, you lose track of them. Debugging experimental models is very hard. Training can be slow. You can run out of memory, or you can build a cool state-of-the-art model, but there's no code in GitHub. Then especially in large organizations, just starting to experiment can be a struggle just to get your data access or service access, or you have some restrictions in the dev environment, or there's some firewalls, and like that can even block you for months before running the first experiment, right? And then if you look at the industrialization phase, that has its own unique challenges. Again, looking at from startups to large organizations, startups typically struggle when they want to put something live. They don't have any infrastructure yet. So you're probably, if you want to put something live, you're also the first one to set up their infrastructure. They have small or no engineering team. There might be just a team of 2 data scientists and that's it. There's a lot of manual retraining going on. Concept drift is also a problem. It's the notion of your model being performant once, but then if you don't retrain it, you see that its performance starts drifting. But again, you need to do a lot of retraining. There is a need for a batch versus request reply inference of your model. You need traceability. CI/CD integration is typically something that pops up. And then at larger organizations, you sometimes see like this throw it over the wall mentality, where a data science group has done a lot of fun stuff in a sandbox and then just throw it to the engineering department to bring it live for them. There's a lot of inflexibility in the compute environment. You have to integrate with legacy systems. Just name one, SAP. If you have to integrate with SAP, that will set you back 3 months, in my experience. You have a lot of technology stack in fragmentation, so that's all quite annoying. And if you actually look at it, this is a study from Google, a paper about hidden technical debt in machine learning systems, is that actually, if you think about it, if you're a data scientist doing experimentation, your actual ML code is really only 10% of what you're doing on a day-to-day basis. You're much more time spending on all the other things in your system. So that's something to be aware of, and you as a data scientist probably know this, but also to communicate to your management that, hey, it's not because you hire 3 data scientists that all we do is going to churn out models, right? There's a lot of other things that we need to do. Google has published another paper about levels of maturity in ML ops, what they call it. Well, it's another buzzword, so now everybody's doing ML ops. Read the paper for more details, but they say, hey, ML ops level 0 is that you manually build and deploy everything. Then you can go to level 1, where you have automated machine learning pipelines. And then level 2, it's quite complex, is you have integrated CI/CD and automatic retraining and concept drift detection. So you see the moment your model starts underperforming, it re-triggers a training job, and if the training job results in a model that's better than the model you have, it's automatically swapped out in production and whatnot. in our experience, we see quite a lot of clients. I think most clients we see are at level 0, and some of them are at level 1. I don't see a lot, if all, clients at level 2. So don't be afraid, don't panic now if you think like, oh, the only thing I'm doing is level 0. That's fine, right? But you know the road ahead. So coming back to that chart, like the way forward, start with experimentation. What could that look like? And we've plotted an example here on this chart. It doesn't have to be exactly this, but it should give you an idea of what to start with first. So if you have a business problem you want to solve with machine learning and you want to go all the way to industrialization, you can start with very simple things like you just open a notebook, start hacking away. You use AutoML. By the way, more and more problems can be solved by AutoML, right? And if I don't have to worry about very basic algorithms, I can just solve with AutoML, and I can focus all of my time on the 20% of the sexy use cases, then do AutoML, right? Don't be intimidated by it. Even drag and drop tools, I'm really not a fan of that, but if you drag and drop tools help you do the experimentation phase, like validate, yep, I have a good model, I have a good business case, do whatever it takes to get up on the y-axis here. Next step is that you can start considering a model registry. What is that? It's just a database to store all your models in. So you can keep track of which models you trained when and which ones are live, which versions have they, and you can quickly find them back in your registry. As a next step, maybe you can do is like instead of having all your hack together code in notebook, you start thinking about modular data pipelines. So you build distinct blocks, you unit test them, you deploy them separately, you put them nicely in Git, you version control them, you peer review them, like all the engineering goodness that you can do with a pipeline. Then maybe instead of just having a model run somewhere in your own system, maybe you can offer your model as an API. So other parts of your organization can call the model through an API, through an inference API. And that's a nice interface that you build between you and the rest of the organization, because they don't have to care how you built your model. They only have to understand your API. And then if you switch a model from Python to Spark to R to I don't care what, they don't even see that, right? They only talk to the API. And then finally, as a let's say, if you really want to be mature in industrialization, if you can integrate your model training and your model deployment with a CI/CD pipeline, you're doing better than 99% of the data science teams that I've seen out there. So it's really cool. And it's also really, when is this helpful? Not if you have a very simple model and it only needs retraining once every quarter or something, nobody cares. But if you have a very dynamic model, which is accessed a lot in real time and actually creates a lot of business value, then you want to really tune it to perfection and make sure that it's always the latest and greatest model is in production. As you progress, typically what you see, your cloud knowledge goes up, because this is kind of implied, but I can definitely recommend do all of this in the cloud. Don't do this on laptops, don't do this on-premise hardware, do this in the cloud. You have to learn about cloud, so it's not free. Your machine learning knowledge will go up as well, and also your dev maturity, like your data engineering maturity, will also grow over time. But most importantly, the business value that you create should also grow over time, right? So never come in a case where you need 6 months or a year before the first piece of business value is delivered. Like, nobody has the patience. Watching my time here. So yeah, then we did a small comparison. We don't have enough time to dive into that here, but we did a small comparison of Azure ML, SageMaker, and GCP AI platform. If you're interested in the full comparison, there is a video out there if you look for the Data Minded channel. And there's actually Bruno presenting it, and Bruno does a much better job than I do because he actually understands, he works with these things day to day, I don't. So definitely look him up or look the video up, maybe as a quick show of what it looks like, what it could potentially look like. I'm just gonna open SageMaker. My computer is slow, yeah. Azure ML and GCP AI, they look kind of the same. So what can you do in these, how can these tools help you in industrialization? Well, many of the things that I just explained, they're available here, right? So things like having a notebook instance or running training jobs, or hyperparameter tuning jobs, building models, having like these API endpoints, batch transform jobs, they're all available here. For instance, if you want to get a notebook, it's pretty cool. You just click a box. I just opened this one, but this is a GPU-enabled Jupyter Lab thing. So I can just open that and then start in my experimentation phase, start hacking away here, right? So it takes a few minutes to load, but it's very nice. We definitely recommend, once you've done experimenting and you know what you want to do, get out of that notebook environment again, right? But here it's pretty cool. You can say, hey, I want to do, I don't know, what is this, TensorFlow 2. So you click and you can start hacking away TensorFlow 2. So let's see if that works. Hello, DS Leuven, and then run it. And it doesn't work. Awesome. Maybe it's still starting up. I don't know. Nice demo. What you can also do here is, if you look at the things here, is that, for instance, the training algorithms here, you can say create an algorithm. You can also specify, was it here or was it, you can also specify just take an off-the-shelf algorithm or use your own algorithm, right? You can find algorithms here. There's even a models package page, and that's also coming back to the AutoML. You just take things off the shelf, right? And if you can take things off the shelf, like a vehicle detector from Hermes, I have no clue who they are, they're probably better than your own vehicle detector algorithm, right? So this is just a quick example, because I don't have crazy much time. It's just a quick example of all the things you can do with a SageMaker thing. So definitely look at these tools that can help you accelerate your industrialization phase and your experimentation phase, so you spend less time fiddling with infrastructure and more time focusing on your business problem. Yeah, so it's actually a false dilemma between the three. They're actually all three quite good. So they offer the same basic set of functionality where we just went through. Like, they have notebooks, they have training jobs, they have hyperparameter tuning jobs, AutoML, and also they offer all these nice things for industrialization, right? I'm going to quickly skip through those. In the end, so choosing between these three is a bit a redundant question, because nobody would ever change their cloud provider just because the ML platform on one provider is better than the other. So if you look about it feature-wise, they all go in the same direction. So maybe now one has the advantage over the other, just like today Audi releases a new car and it's a bit better than the Mercedes, and then over 3 months Mercedes releases a new car. But in the end, they're all very similar. What you have to be careful with, though, is that the 3ML platforms can get very expensive as you scale. So if you look at large-scale enterprise deployments across teams, there it might make sense to take back a bit more control in your hands and manage things yourself again. So yeah, be careful if you're in a large organization. Yeah, just as a general recommendation, so for experimentation, pick whatever tool you're most comfortable with. Look at whatever the cloud provider has to offer. Focus on fast iteration, self-service, and easy debugging. Then when you want to do industrialization, look for integrating with existing stable data engineering chains, so make sure it fits with the rest of your systems, especially for enterprises. For startups, start with the deployment options of these ML platforms, like the batch inference and the API inference that they have, and focus on reliability, traceability, and also, especially for big companies, avoid technology fragmentation, right? Because it's really cool if you know, I don't know, TensorFlow really well, but if you're the only one in the organization who knows TensorFlow, and then the next wants to do something in Go, and then R, and then Julia, and then like all of a sudden you have 10 languages and 3 engineers or 3 scientists have to support that. That's really, yeah, you should avoid it. Also, if you're a startup, when the costs become too high of these ML platforms, when you start having data permission issues or instabilities, then it would make sense to look at building it yourself, because these things have a lot of features, but they're not super stable. They're in flux still. This I'm going to skip because I'm out of time. Let's see if there are questions.
Not only super. Mute somewhere.
No, you're not on mute. I can hear you, Istan. Go for it.
Yeah, but there's an echo.
I'll mute myself maybe.
Yeah. Okay. Anyways, let's have a look whether there are questions, and otherwise I have one myself. That there's a lot of not really questions. So let me, while people are preparing their questions, just ask them a more general question that goes maybe beyond your presentation as such, but it's something that I've been wondering about. So if I understand you correctly, the whole story is basically advice you give based on the experience you have had over the last couple of years. And you made a distinction between startups and large organizations. So I'm mostly interested in the large organizations. Don't ask me why. Now, I imagine that there are two types of large organizations in let's say, especially within, let's say, your clients, so to speak. You have large organizations that basically where anything which is related to data as such is essentially absent. They might have an IT organization, but they don't really know what to do with it. So basically you have a blank sheet of paper. That's one type. The other type is where they might have a BI team, and they might have maybe even a newer data science team and so on and so forth. So from your perspective, I would guess that the second one is more mature in a certain sense, but I can, on the other hand, also imagine that the first type of client is easier to work with. So can you tell us something about that?
Yeah, there's no right or wrong here, but I'll just give you my experience and my opinion. Having a BI department or not, and that can be valuable in its own right. BI, there's a lot of valuable BI use cases, but having a BI department is completely orthogonal to whether you're being productive on data science. Because what we typically see is different profiles in the two departments, solving different needs for different kinds of parts of the organization. So what I would recommend for large organizations, if you have a blank sheet, start with low-hanging fruit. So bring one use case all the way to production and make sure it starts bringing you money. And then with that money, you can say, now I need to start up, I need to have a data platform, and I need to have more data use cases. And then once you mature that, you can also consider, maybe now it makes sense to more integrate the BI and the data science departments, because in the end, they're both very data heavy workloads. And whether you do it on a data lake or on a data warehouse, honestly, nobody cares. So try to find synergies between the two departments, but if you have a blank sheet, don't say we're going to build a perfect big data platform and migrate BI to that, and then we're going to do a data science use case, because then you're up for this like 3-year project that's going to cost you millions, and you're going to get shut down sooner or later.
Okay.
I hope that answers your question. But yeah.
Yes, it does. Okay, let me see. No questions for the moment. So then we'll just we have still 5 minutes, and we're going to use the 5 minutes. So from your perspective, so regardless of what is good for the organization, which type of, what do you like personally? Let's say the clean sheet of paper, or rather the more evolved kind of organizations? Which is more fun, so to speak?
Yeah, no. The organizations I like best, but this is very personal, is the one organizations who are ready to go to the cloud. So I don't want to get involved in any on-prem data science project. And it's just because I know I've seen this a million times, we can be 10 times more productive in the cloud. And I don't care which cloud, but a cloud. So that's one thing that I want to see. And another thing is, I want to see a business department being very eager and very anxious to get this a use case live. Because if it's an IT-driven project, then I'm usually worried, like, yeah, we're going to do fun engineering stuff, and in the end, it's going to be shelved. So I want to see a hunger in the data in the business teams, because I know that gives most long-term success. It also creates most stress, but that gives most long-term success. So those two things I'm looking for. Are you in the cloud already? Are you willing to go to the cloud? That's one. And two, are your business teams anxious to get this live?
Okay, that's clear, and that makes sense to me. So, unless something is, well, I have to conclude that your presentation must have been very clear, because there are no questions. So I would say
it's either everybody understands it or nobody understands it, right? That if there's no questions.
yeah. We'll see. or maybe they just want to know what the government is deciding with regard to the possible lockdown. Or
I
whatever
see
they are
a
discussing.
question from Alexander, like, hey, which classifier do you see the most? Well, but again, this is one data point, Alexander. So if you ask another consultancy, they will say something else. But we see AWS the most, and then Azure, then Google. But yeah, I mean, if you talk to Element 61, they will see Azure the most. If you talk to ML6, they will see GCP the most, right? So, yeah. But I don't think it's contentious to say that AWS has the largest market share, right? They are the biggest cloud provider. It's just a fact. But they're all three of them are good, right? So don't stress out about any of these three. They're all good.
Okay, good. Well, I hear that it's very insightful, so that's all good news.
I have to answer that one. Do you
Okay,
prefer
go ahead.
Python or R? Definitely, like by a long, and I don't know if this was like an open goal that you wanted me to score, but by very far, Python. Like there's no discussion. Python is orders of magnitude better in my eyes. I know R, you might have a few statistical libraries that you're missing in Python, but I really don't care. I haven't seen a lot of R applications being productized or being industrialized successfully. I'm sure it's possible, right? If there's some R expert listening, I've done it once for sure. I haven't seen it a lot. With Python, you can do a lot more, and it's a lot broader language. So I'm a big Python fanboy. But yeah, I'm biased. Again, I'm very biased, but yeah.
Right. Okay. It's an interesting question, and especially if you ask it 1 minute before we have to close down. Anyways, so with this, I would like to thank Chris for being such a good sport to resolve our problem after the cancellation. Nonetheless, I still hope that we'll get a repeat, or not a repeat performance, but that our original guests will be able to join at a later occasion, because I think it was I read their paper and it was quite interesting what they were doing. So thank you again, Chris. Thank you, Philip, and thank you, Tim, for very interesting presentations. And thank you, Lean, for taking care of all the technical issue, or let's say technical issues that we've had. And I think we're learning as we go ahead, and as it looks like, I think we'll need the experience, because I don't think that the next couple of months we'll be doing face-to-face meetings again. But we're learning all the time. And with this, thank you again, and thank you for listening in, and see you next month. Bye.
Bye, everyone. Thanks. Bye.
Bye.